Dropout is one of the most influential regularization techniques in modern deep learning, and despite its apparent simplicity, it captures several deep ideas about generalization, model averaging, and noise injection in high-capacity neural networks. To understand dropout properly, it helps to begin from the broader context of why regularization is needed at all in artificial neural networks. When we train a neural network with many parameters on a finite dataset, the model has enough capacity to memorize the training examples rather than learn patterns that generalize to new data. This phenomenon is called overfitting. In overfitting, the training loss becomes very low, but the validation or test loss remains high. The network has essentially learned idiosyncrasies of the training set rather than the underlying data generating process. Regularization techniques are designed to reduce this gap by constraining the model in ways that encourage more robust representations. Dropout addresses overfitting by introducing stochasticity directly into the network during training. The core idea is straightforward. During each forward pass in training, a random subset of neurons is temporarily dropped out, meaning their outputs are set to 0. The selection is independent for each mini-batch and typically follows a Bernoulli distribution. Each unit is kept with probability p, often called the keep probability, or equivalently dropped with probability 1 minus p. At first glance, this might seem like a crude intervention. Why would randomly deleting parts of the network help it learn better? The answer lies in the way neural networks co-adapt. In a standard fully connected network without dropout, neurons can develop fragile codependencies. One neuron may rely heavily on the presence of another specific neuron. The network can form narrow, brittle pathways that work well on the training data but fail to generalize. Dropout breaks these co-adaptations. Because any neuron might be removed on any given training step, the network cannot rely on specific partners being present. Each neuron must learn features that are useful in many different sub-network contexts. This encourages redundancy and distributed representations, which tend to generalize better. Mathematically, dropout can be interpreted as training an implicit ensemble of many subnetworks that share parameters. Each dropout mask defines a different thin network. During training, the optimization process updates shared weights so that many such subnetworks perform reasonably well. At inference time, when dropout is turned off, the full network approximates an average over this ensemble. This model averaging perspective is one of the key conceptual insights behind dropout's effectiveness. To make the mechanism precise, consider a layer output vector H. During training with dropout, we sample a binary mask vector M where each element is drawn independently from a Bernoulli distribution with parameter p. We then compute the dropped output as H multiplied elementwise by M. In many implementations, we also scale by 1/p during training so that the expected activation magnitude remains unchanged. This is often called inverted dropout. The scaling step is important. Without it, the expected total activation would shrink during training and then jump at inference time when dropout is disabled. By scaling during training, we ensure that the expected value of each unit remains consistent between training and inference. This makes optimization more stable and avoids needing special handling at test time. From an optimization perspective, dropout introduces multiplicative noise into the network. Noise injection has long been known to act as a regularizer. It smooths the loss surface and discourages sharp, highly specialized solutions. One way to think about dropout is that it perturbs the network differently on each mini-batch, forcing the optimizer to find parameter regions that perform well under many perturbations. There is also a Bayesian interpretation of dropout. Under certain assumptions, applying dropout during training and inference can be viewed as approximate variational inference in a deep Gaussian process. In this view, dropout induces a distribution over network weights and outputs, providing a rough measure of model uncertainty. While this interpretation has limitations, it provides useful theoretical grounding for why dropout can improve generalization. In practice, dropout is most commonly applied to fully connected layers, though it has also been used in convolutional and recurrent architectures. In convolutional networks, spatial dropout variants may drop entire feature maps rather than individual activations, preserving spatial coherence. In recurrent networks, naive dropout can disrupt temporal dynamics, so specialized variants such as variational dropout or recurrent dropout are used to maintain consistent masks across time steps. Choosing the dropout rate is an important hyperparameter decision. Typical dropout rates range from about 0.1 to 0.5 depending on the layer and model size. A higher dropout rate provides stronger regularization but may slow training or cause underfitting if too aggressive. A lower rate may provide insufficient regularization. In very large modern models, especially transformer-based language models, dropout rates are often relatively modest because other forms of regularization and large dataset sizes already help generalization. It is also important to understand where dropout is typically placed in the network. It is most often applied after nonlinear activations in hidden layers. Applying dropout directly to inputs is sometimes useful but must be done carefully because it effectively corrupts the data. Applying dropout to output layers is usually avoided except in specific cases. In transformer architectures, dropout is often applied in attention weights, feed-forward sublayers, and residual connections. Another subtle but important detail is the interaction between dropout and normalization layers. Batch normalization, for example, introduces its own form of stochasticity and regularization. In some architectures, heavy dropout combined with batch normalization can lead to diminished returns or unstable training. Modern practice often uses lower dropout rates when strong normalization is present. From a historical perspective, dropout was especially important in the era when neural networks began scaling up but datasets were still relatively limited. It provided a simple, computationally cheap way to reduce overfitting. As models and datasets have grown dramatically, the relative importance of dropout has shifted somewhat, but it remains a standard tool in many architectures, especially when data is limited or models are prone to memorization. Dropout also interacts with model capacity in interesting ways. In some sense, dropout allows practitioners to train larger networks than would otherwise generalize well. Because many units are randomly disabled during training, the effective capacity seen by the optimizer on any given step is reduced, while the full capacity is available at inference time. This can be viewed as a form of capacity smoothing. There are several variants and extensions of dropout. Drop Connect randomly drops individual weights instead of activations. Alpha dropout is designed to work with self-normalizing neural networks. Variational dropout introduces a learned dropout rate. Zoneout applies stochastic identity connections in recurrent networks. Each of these variants attempts to preserve the core regularization benefits while adapting to specific architectural needs. It is also useful to understand when dropout may be less effective. In extremely large-scale pre-training regimes with massive datasets, the model may already generalize well without strong explicit regularization. In such cases, heavy dropout can sometimes slow convergence unnecessarily. Similarly, in architectures that rely heavily on residual connections and normalization, the marginal benefit of dropout may be smaller than in older fully connected networks. Another important consideration is that dropout is only active during training. During inference, the network operates deterministically with all units active, using the scaled weights learned under dropout noise. This difference between training and inference behavior is intentional and central to the ensemble interpretation. However, it also means that training dynamics can be noisier and require careful tuning of learning rates and schedules. From a geometric perspective, dropout encourages the model to find flatter minima in the loss landscape. Flat minima are regions where small parameter perturbations do not drastically increase the loss. Such solutions are believed to correlate with better generalization. By randomly perturbing the network structure during training, dropout biases optimization toward these more robust regions. In modern transformer-based language models, dropout often appears in several specific places, after attention softmax, within feed-forward layers, and on residual connections. However, as models scale and datasets grow, many large production systems use relatively small dropout probabilities, relying more heavily on data scale, weight decay, and architectural inductive biases for regularization. One practical debugging insight is that if training loss is much lower than validation loss, increasing dropout may help. Conversely, if both training and validation losses are high, the model may be underfitting, and reducing dropout could improve performance. Like most regularization tools, dropout must be tuned in the context of the full training setup. Another subtle point is that dropout increases gradient noise. This can sometimes help escape sharp minima early in training but may slow final convergence. Learning rate schedules, warm-up strategies, and optimizer choice can interact with dropout in non-trivial ways. Empirical experimentation remains important. From a conceptual standpoint, dropout embodies a broader theme in deep learning. Controlled stochasticity can improve generalization. Rather than seeking perfectly deterministic training dynamics, we often deliberately inject randomness through mini-batch sampling, data augmentation, label smoothing, and dropout to encourage models to learn more robust representations. Even though dropout is simple to implement, its impact on the development of deep learning was significant. It provided one of the first widely adopted, effective regularization methods that scaled well to deep networks. Many subsequent techniques build on the same intuition of preventing fragile co-adaptation and encouraging distributed representations. As the field continues to evolve, dropout remains part of the standard conceptual toolkit for understanding neural network regularization. Whether or not it is heavily used in a specific modern architecture, the principles it embodies, ensemble thinking, noise-based regularization, and robustness through stochastic training, remain deeply relevant to the design and training of high-capacity AI systems.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.